Okay, good morning again. Remember to profit from any opportunity that you may have to expand your vision, meet the job market, meet interested companies, agencies. It's never too early. And, you know, sometimes profiting from an opportunity makes a big difference. Sometimes it's really a spot idea that may change your career. And of course, it's opportunities are many. It's not only one. So you have to make a selection. So don't be afraid if sometimes you cannot profit from an opportunity. You will have many others. The important thing is that you make an effort to not to miss them. And the best way not to miss an opportunity is not to underestimate your capabilities, your skills. Sometimes it happens very frequently to me as well. We think, okay, this is not for me because I'm not good enough. And yeah, I would say that it's everything is possible if we want. It depends on the will. So, and of course, taking opportunities means also the fact that you may be disappointed when they don't materialize, but that's life, and you have also to learn not to get disappointed. Of course, when your target is very high, the probability of success may be very low, and in this case, we just have to understand that we don't have to be disappointed when we don't succeed in an opportunity where probabilities of success are low. Now you know what is probability, so you understand what I mean. Okay, very good. But I know a lot of people who succeeded in challenges with a very low probability of success. Of course, I know more people who didn't succeed, but I also know a lot of people who succeeded with very, very low probabilities. So I think, you know, everything is possible. Okay, very good. Now let's move forward. And today I will teach without PowerPoint, but using the Blackboard. And I will take care of focusing the screen and the recording of the video on the Blackboard. I didn't do that in past lectures, but before I start with the Blackboard, let me share the screen actually, and let's look at where we are now. So let me go back on page. This is our web page, which I changed with the addition of one lecture yesterday night, so you didn't see it probably. It's called Inductive and Deductive Estimation of Climate Change and Climate Impact. And the order of the links now should match the chronological order of my lectures so far. As you see, we are more or less at half of our joint adventure. Some links will be removed, other links may show up like I did yesterday. Actually, what I included yesterday is just a modification of something that was already there. Good. So what are we talking about today? Today we are getting into the problem of, or let's say we are getting more in detail into the problem of quantitative estimation of climate change and climate change impact. Why quantitative? Because we already learned that in engineering design, or in order to take actions, we need numbers related to climate change. Awareness is just not enough. Let me try to turn the light off. Awareness is not enough, we need numbers. Okay, that's fine. And then we already focused on risk, on the concept of risk. One way of quantifying the impact of climate change is through risk estimation. And we already discussed risk estimation. Precisely for the very reason that we want to get numbers. Okay, and then today we are focusing, we are just going into more details into risk estimation. Okay, so we start with, I start today with the risk equation, which you already know. R is equal to the product of hazard P vulnerability V, and exposure E. We already know the details. There are links in my webpage to what we already discussed. So we already know that what is hazard, which is probability of a threat to materialize, defined in whatever way. We know that probability can refer to discrete or continuous random variables. And then, depending on the nature of the random variable, if it is discrete, it's easier to estimate probability. If it is continuous, it's a little bit more difficult, but it is something that we now know how to do. We know how to estimate probability. And then we also discussed vulnerability and exposure. We discussed with more details probability, but we left open one question, meaning that we discussed how to estimate hazard probability when we have numbers, when we have observations, when we can make an experiment that allows us to collect the numbers. And the experiment may be to go to the Regional Agency for Environmental Protection and get some historical data. Some data on forest fires, earthquakes, temperature, rainfall, river flow. This is the result of an experiment, because any observation, any number that we collect on the field is an experiment. It's like tossing a coin or rolling a dice. Okay? And so we know how to estimate probability when we have these numbers. But under climate change, we refer to the future. We need numbers for 2050. We need numbers for 2100. And then we said this is a challenge because we don't have observations for the future. And then we said we can use models. We can use models, and we discussed a little bit how models can be used. Okay. Today, I want to focus more in detail on this challenge, future experiments, future climate, future probabilities. Future probability means future numbers. How can we get temperature observation for the future? How can we get rainfall for the future? These are called, these information related to the future are called climate scenarios or climate projections or climate predictions. How can we elaborate the climate information for the future? Let me admit one more student. How can we get this information for the future? Of course, making prediction is always difficult, especially when it refers to the future. This is a very well-known say, it's not mine. And future predictions, it's always a challenge, especially if we make predictions in a changing situation. Okay, let's see then how we can move forward, and we can recognize, we already discussed this, we can recognize two methods. There is, these two categories of methods are the deductive assessment or the inductive assessment. Inductive means that I try to learn from the data. Deductive means that I try to learn from the theory. Let me focus a little bit on terminology. I said climate scenarios. So when you listen people talking of climate scenarios, usually means future predictions, future pictures of climate. But people also use the term prediction or projections. In my opinion, the correct term should be prediction, because it is actually a guess of what the future will be. Projection is used as a synonym of prediction, so just be aware of that. When you listen about projections, it's the same as predictions. Once again, I insist on terminology because I suppose that in the future you will have, during your career, the need of studying more. And knowing the terminology makes your additional study very much easier, very much easier. Because sometimes, you know, when you start reading something and you really don't understand what the PDF or the information or the website is talking about, it's really discouraging. Because one thinks like, I really don't know anything about this. Actually, very often, you know what they are talking about, but you just don't know the terminology. So like if you look at, this happened to me, I look at some website, climate projections, what is a projection? I don't know really anything about this. And then I realized that projection is a synonym of prediction. And you may ask, why did they introduce the term projection? Because they wanted to emphasize that there is a lot of uncertainty in climate predictions. And therefore they wanted to distinguish the prediction of climate from the prediction of weather, for instance. And the idea was that prediction is more quantitative than a projection, but actually it would be better to use an easier terminology. Projection are predictions with higher uncertainty, that's fine, but they are prediction. Any prediction is uncertain, so there is no reason for calling a prediction with a different name if uncertainty is higher. It's just a prediction with higher uncertainty. And also be aware of the difference between climate scenario and weather scenario. You know the difference between climate and weather, okay? We don't repeat it here. So when you listen to somebody talking about weather scenario means everyday prediction. Climate scenario means a prediction of statistics. You know that climate is statistical weather, okay? Okay, so there are two methods, and let me start writing on the blackboard, and let me try to, let's see if I can do like this. I think that now in the recording there should be the blackboard big and the screen small. Let me use the other camera. Okay, good. 1 second. Let's hope that it works here. Okay, so remember R is equal to PVE, and here we are estimating here hazard or probability. Good. Probability. And we said two categories, so we go here and we have inductive methods, deductive methods. Deductive methods. Here I can write data, and here I can write theory and models. So basically, with inductive methods, we use observations, of course not future observations, past observations, to predict the future climate. With the deductive method, we use the theory of physics, the theory of atmospheric sciences, the theory of hydrology, in order to elaborate an analytical prediction of the future. So what is the difference between the two approaches? With the first one, I extrapolate into the future what the data tell me, what the data that I collected so far tell me. With the second approach, I extrapolate into the future what the theory tells me. You may think, based on this definition, that the two approaches are much different. Actually, they are complementary and not very different, because in validating the theory, in validating a model, in understanding if the model is correct, I may use data. So there is an overlap between these two categories. But the essential difference is that with the first one, strictly speaking, I don't need a theory. I don't need to understand the dynamics generating the data, strictly speaking. With the second one, strictly speaking, I don't need data. I can elaborate a prediction even without any observation. And then, of course, in practice, I anticipate to you the conclusion. What I need to do, what I will try to do, is to merge the information that I can derive from these two approaches. When we talk about climate change, when we talk about something that actually we don't know, we need to put together all the available information. So we need to make use of data, we need to make use of model. So I don't agree, I don't like the interpretations, the extreme interpretation of some researchers who say models are better, models are more reliable, let's forget about data. And as well, I don't like the interpretations, models are unreliable, models are uncertain, let's forget about models. These are extreme positions which tend to neglect, tend not to use part of the information. What we need to do in practice, what we need to do in order to design actions to adapt to climate change, is to use all the available information. It's a different story with respect to research, to understanding what's going on. One thing is understanding, one thing is elaborating a theory. Another thing is to take action, is to adapt in practice. You know, in the second case, you deal with people, you deal with a socioeconomic setting. If you make a mistake, it's a problem. You deal with disasters that kill people. So you understand the approach is different. And in this second case, where, by the way, the engineer bears a responsibility, it's extremely important that you use all the valuable information. On the other hand, it's very interesting for us to understand how they work, these methods. And both of these methods can be used to reconstruct the past climate. Keep in mind, we are talking about prediction. This is our target. But we can also use inductive methods and deductive methods to reconstruct the past climate. We discussed a lot on how the climate changes into the past. Understanding the past is the key for making future predictions. So these methods can be used for reconstructing the past climate, reconstructing the future climate, and making impact assessment. And let me try to clarify what is the difference between predicting the future climate and predicting the impact. So the impact is given, for instance, by a flood and or by a drought, while climate typically refers to the driver of these disasters, which is rainfall. So when I talk about climate prediction, usually, or climate change, usually I talk about changes in rainfall, changes in temperature. I don't talk about changes in droughts. So climate refers to climatic variables. when we turn to impact assessment, we need to focus on the variables who generate the impact, which may be, for instance, dry days. For a drought, it's dry days, consecutive dry days. And very often I need to use different models. I need to use different data in some cases, okay, because I can use socioeconomic data, for instance. If I want to quantify the impact of a disaster, I also need a socioeconomic assessment. So you understand that it's a step further. So when I talk about impact assessment, usually I need to consider climate change at the beginning, and then use an additional model, like a socioeconomic model or an hydrologic model, which uses the information from the climate change model and then further elaborates. So these methods, inductive and deductive, refer also to these further models, to this further step. Impact assessment is very exciting because it actually allows us to understand the effect on people, and it allows us to understand adaptation actions and mitigation actions. Impact assessment is, I would say, to me looks as the most exciting part, because we come to people, we go to people, and we have the opportunity of proposing solutions. So the moral of the story is that there are different models and maybe a cascade of models. You may have a climate model, so climate model, and then here you have an impact model, and then you may have again a socioeconomic model. So you may have a kind of cascade of assessments. And this can be done through inductive methods or deductive methods. For instance, if I want to estimate the impact with an inductive method, I may look at past disasters and look at the damage caused by these disasters and make a prediction on how these damages will propagate into the future. And the prediction may be done without any understanding of the dynamics of the impact, just looking at past damages, past number of people who died, and then we make a prediction. Very often, you may find a report on climate change basing on the losses. You see graphs of losses. I want to give you an example. There is a, and this is inductive. I want to give you an example by going to a website, which is the website of Munich Re. I think I already mentioned to you this website. Munich Re is an insurance for insurance company. And their mission is to understand the risks that they are insuring. And basically, they are insuring insurances, which means that when the insurance needs to get in turn insured, because of course, when we get insured against the damage, we want to be guaranteed, we want to give a reassurance that even if the damage is a disaster, the insurance company can provide the refunds to us. And therefore, in order to give this reassurance, insurance companies need to get reinsured in turn. And the Munich Re is not insuring people, they are insuring insurances. And therefore, they are much interested in getting an understanding of what's going on after climate change. And their method typically is based on data analysis. They also look for inductive and deductive approaches, but they first want to look at data. So here, if you click on risks, there are several risks which they insure. So you see here natural disaster, losses are trending upwards. So let's try to click here. And here there are the natural disaster, flood risk, or let's take something different because I am biased, earthquake, okay? Let's see what's going on here. Earthquake, loss prevention, that's just 1 second. Here you see a number that is going on, but there are graphs. Oh, okay. These are the 5 largest earthquakes, 1990, 2022. And you see the horizontal axis. I don't understand. There is no caption on the horizontal axis. I think it is damage, not because it can't be loss of lives. So probably it's damage in billions. And you see here the 2018 Tohoku earthquake off the coast of Japan remains the costliest natural disaster of all time, with overall losses of US 210 billions, which is this one, I think. No, it's 2004. I don't sure. Okay. This is let's see. This is fatalities. Okay. This is the losses. Perfect. So these are fatalities, and it's really many. Amazing. And these are losses. This is an example of a graph. You see, they look at data. They look at data. Keep it in mind, because they are working in practice and they trust data. Let's look at another graph, like flood risk. And here, I think somewhere there is river floods. Let's see. Okay, I don't find the graph, but here there is also a graph who shows the progress in time of the damage due to floods in Europe and at the global level, which is another demonstration that they work on data. And I think risks. Okay, we need to move forward, but I just wanted to give you a demonstration, okay? Good, let's go back here. Okay, now, let's give a couple of examples of these two methods in order to understand how they work and to understand how we can couple them together, how we can merge the information from both of them. We cannot provide several examples, so I will refer to examples that are very frequently used for inductive and deductive methods. So for inductive methods, let me give you an example of analysis which are frequently carried out in order to understand climate change. So we focus on the first step here. So inductive methods for understanding, quantifying, and predicting climate change. Okay. It's very frequently, an example that is frequently cited, mentioned. And the first example of inductive method is trend analysis. So let me just write here. We are talking about hazard, probability, and inductive methods. Inductive trend analysis. In trend analysis, you get a picture of observations, like, for instance, global temperature, global T. Global T, you know, because we discussed it several times, starts usually from 1850 up to 2023, 2022. And let's say global T at annual time scale, annual. And then what you see is, let's see, if half of it is about 1930, this is, okay. So you see that there is a first part that, as we remember from the graphs, that goes up, and then we have a decline, and then there is a sharp increase recently. The graph that we observe of global temperature is something like this, okay? Probably it's steeper, so let me just correct it a little bit, because it's actually steeper than that. So there is here a hiatus, and then, okay, it's something like this, okay? This is global temperature. So we see that there is an increase, but we need to quantify this increase. And then we need to quantify this increase and project it into the future. So we need to make this prediction. And here we have the question mark. So what could be a way of solving this task? A way is to fit what we observed with an analytic curve. An analytic curve allows to make an extrapolation in time. This is what we do also with probability functions. What I said is I estimate frequencies, but it's better to have an analytical representation of these frequencies, because when I have an analytical function, I can use it in order to explore the unknown. So what could be an analytical function to represent an increasing tendency? There are several analytical functions that can be used. What is frequently used is the linear interpolation. Linear interpolation. Linear means that I use a straight line to represent this increasing trend. A straight line. Okay, so linear interpolation is a straight line. Good. Now, what is the expression of a straight line? So if I indicate the global temperature with the symbol T, okay, this is my global temperature, and time is T, I can write the straight line with the very well-known formulation T is equal to A plus B T. But this is not precise. I cannot reconstruct very precisely temperature with a straight line. So I need to write here an error term plus epsilon T. Let me indicate T as a function of time here, okay? And here I put T. So the temperature is expressed as a function of time, and then I see the independent variable time here, and here I need to add an error. Okay, this is an error term. Error term. Good. This error term represents uncertainty. Okay, uncertainty. Perfect. And if I make this estimation here, the result probably will be something like this. It's a straight line which has to find a kind of midway along the observations. And this is my A. The intercept. Okay. Good. Here in this equation, time is progressing starting not from 0, it's starting from 1850. Okay, it's a number of years from 1850. Because here you see that my purpose is to reproduce from 1850 to 2022, and therefore here time starts from 1850. Okay, let me just put in evidence here from 1850. Good. Remember what is a linear function. A linear function is represented in a graph through a straight line. A linear function satisfies two requirements, two conditions, necessary and sufficient conditions. So if a linear function, let me write it here. If I have a function f(x), which is linear, I have two conditions to be satisfied. F(x) is Rfx, and 2f, we use the same symbol for f. Here it is, and here it is. Okay, fa plus b is equal to fa plus fb. Okay, a linear function satisfies these two conditions. Remember them. Okay, this is maybe a classical question for a quiz. Okay, it's important that you understand the difference between linearity and nonlinearity. So here we are talking about linear interpolation. It's using a linear function. Okay, now you see that this function is characterized by two parameters. What are the parameters? Are, in this case, constant coefficients, which don't change the shape of the function because it remains a straight line, but change its position with the intercept A and its slope with parameter B. Parameter B is the slope. Okay, you understand that in this case, if B is 0, you don't have change in time. You don't have climate change. Okay, if B is 0, you don't have climate change. If B is positive, you have an increase of temperature along time. If B is negative, you have a decrease of temperature along time. So you understand now why this approach is often used to detect climate change. People typically fit the data with a straight line and look at the value of B. If B is 0, there is no change. If B is positive, there is an increasing trend, and the opposite if B is negative. You see, this is a typical inductive approach. We look at data. We don't look at the theory here because we use a straight line, a linear function. Climate is everything but linear. Okay? Dynamics of temperature is everything but linear. For sure, it's not linear. So we don't look at the theory suggesting that climate is nonlinear. We just look at the data and use a simple model. So our objective here is to use a simple model. You see, this straight line is very simple. It's not a complicated climate model with partial differential equation with the integrals, whatever. It's extremely simple. Two parameters, A and B, which just allows us to shift, to move the line up and down and to make it more steep or not. It's very simple. Why should we then ignore the theory? Why do we make this choice of a very simple approach? Why we discard any theoretical consideration? Because simplicity means very often robustness. It means that the model, the straight line, is not fitting the data correctly. On the other hand, it's not very wrong. Remember that when you use a method for exploring the unknown, especially when you refer to nature, you have limited information. The fact that we don't have many data, it's common when we work with nature. We don't have a good wealth of observations. Very often we have to work with few numbers, which means that you may be wrong. Because when you make predictions based on a limited knowledge, your prediction may turn out to be completely wrong. Okay, it's like when you try to get oriented without a map, you don't have any information on where you are. It's very easy to get wrong, and therefore you need to seek a robust choice, a robust decision. The robust decision means for sure I will be wrong, but I will not lose my life because the decision will not be very wrong. We will discuss again on robustness, which means that you give the first priority to minimizing the damage, not to seeking the best solution. It's like when you invest money in a condition of high risk. In a condition of high risk, you seek a robust investment, an investment that don't bring you to lose all the money. The robust investment typically is not leading to a big income, a big gain. It's just looking at minimizing the potential losses. And even here, it's the same thing. Why do I use a linear model? And I go back to my original reasoning. Why do I forget the theory? Because the theory is complicated. The linear model is very simple. So you see here, I don't make big mistakes. And when I make my extrapolation, I don't make big mistakes. Now, let me give you a counterexample of a model that is not robust. And let's use the same graph. Okay, let me cancel the title here. And let me use the same graph and use an alternative model. So given that I know that the linear model for sure, it's not representing temperature well, because we know that climate is nonlinear, I may choose to a slightly different model, so not the linear one, but another one which could be nonlinear. And in order to get non-linearity, you have to put exponents into time. So what I could do is to add an additional parameter, which is, for instance, an exponent alpha here. If I put an exponent alpha here, if alpha is equal to 1, the model remains linear. If alpha is equal to 2, the model becomes quadratic. And if I then pass to this model on this graph, I use a different color. What I would probably obtain is a better representation of my observations, because the nonlinear model can capture the increasing slope in the last part. And therefore, the nonlinear model probably would give me a response like this. A better representation of the observations, but a completely different behavior when I extrapolate into the future. And into the future, I don't have any means of making checks, of course. So, as an engineer, what would you think would be the safest approach to get a prediction for the future? You see, they are very different, but is it reliable that temperature in the future keeps a steep increase with a slope that is continuously increasing because it's quadratic? Probably not, because we have already actions in place in order to mitigate the CO2 emission, so it is probably not safe using this kind of prediction. It's too precautionary, especially if the cost associated to mitigation depends on the level of change. And then we could end up with something that is not affordable, with solutions that are not affordable. And solutions that are not affordable very often are simply not activated, so we do nothing, like we often do in the presence of climate change. So I have no doubt in saying that it's preferable a robust approach, the prediction given by the blue dashed line. And then if I am not convinced, I could try to use a flexible solution, a solution that can be corrected in the future if something goes wrong. So you see the difference between a robust approach and an approach that may be more theoretically sound, an approach that could reproduce better the past observations, but when we project into the future, it doesn't meet our perceptual prediction. These are experiments that can be easily done, and I am planning to propose you a simple exercise showing the effectiveness of various models to interpolate the global temperature. We have several data available. We can get data of global temperature and see what is the difference between linear interpolation and polynomial interpolation, because we can extend this analytical relationship by adding terms. Okay, now let's go back to the linear case. Here, you have the problem, even under the assumption of linearity, to estimate the parameters of this straight line, A and B. It is very easy. I think you had already some background on linear regression. It's very easy, but still keep in mind that it's easy. We will see in R, it's a matter of few seconds. When you have the data, there is a function providing to you the estimates of the parameters. But you have to take into account that there is always this term, epsilon t, which is a quantification of your uncertainty. and therefore you don't have to just pick up the values of the parameters and make your prediction. You have to look at the result of epsilon t. The larger the epsilon, the larger the uncertainty. The smaller the epsilon, and the happier you are, because it means that the linear interpolation is fine. So you have to look at the error, and actually the estimation methods are conditioned by assumptions on this error. The error has to possess nice features. For instance, let me give you an example. I'm trying to speak with very practical words. Suppose that you look at your errors and you see that they are small, but there are a few of them which are extremely large. You are not happy. You are not happy. You would be happier with an error that is constant, isn't it? More or less constant. So you get also an idea of what you expect into the future in terms of errors. If you get a small error, but in some cases it's extremely large, you know, you are a little bit concerned, because you are concerned that when making your prediction, you experience again the large error, which is not a good thing. And in fact, one of the assumptions, I'm not getting into the details, but I just want to tell you that one of the assumptions conditioning a good estimation of a straight line is that the error is Gaussian. It's normal, follows the normal distribution. This means that the straight line is working well. Normal means that you don't have outliers. It means that you don't have large errors suddenly. Normal means stability. Normal means symmetry, as we learned. So be careful of the error that you make, and be careful of the difference between interpolation error, which is my epsilon, interpolation error, it's my epsilon, and extrapolation error. They are different. When you make a prediction for the future, you are extrapolating. And you always have to associate the term extrapolation to uncertainty. Good. The extrapolation error is always larger than the interpolation error. Always. We frequently assume that they keep the same behaviors. So I'm saying to estimate uncertainty of future projection, often we say we make the same kind of error. Actually, it's not like that. They are very different, and extrapolation is larger. So you have to expect, when you extrapolate, that you get a larger error. And the longer you go into the future, the larger the error that you make, the larger the extrapolation. So the longer you go into the future with your prediction, the longer the extrapolation, the larger the error. This is very obvious, it's an elementary concept. Like I make a prediction for tomorrow, and I extrapolate just a little bit, and the error is small. If I make a prediction to 2100, I extrapolate a lot, I go very deep into the unknown, and uncertainty increases. Okay, now let me go back to the essential concept here with the inductive method. I look at the behavior in the past, I look at the change in the past, and I project this change into the future. This is a possibility. This is a possibility, which is not necessarily more uncertain with respect to other methods, maybe more reliable. And you don't have to think that, you don't have to conclude that this is a trivial and useless approach, because it is very simple. It's an approach. And this is the way usually data and climate change are quantified. If you look at the website of Munich RE, they say they look at the past and they project into the future by assuming that the change in the past will be analogous to the change that we will experience into the future. Perfect. And this is just one example of an inductive method, trend analysis and linear interpolation. I just want to say one thing. The linear model, I used it for representing temperature because temperature is nonlinear, but it's not highly nonlinear. It's not highly nonlinear. Other variables are highly nonlinear and you cannot use linear interpolation. And let me give you an example. Daily rainfall. Daily rainfall has several zeros. Several zeros means that you cannot use this model to reproduce the progress in time of daily rainfall. It's not possible, because how can you represent a zero here? Because, I mean, the straight line, if it starts with a path, with a trajectory, you cannot bring it to zero with a sharp angle. The straight line cannot go once that it started with a value that is different from zero. Okay, you can bring it to zero with a declining slope, but then you reach zero and you go into the negatives, so it's just 1 0. You cannot reproduce a sequence of zero like daily rainfall, 30 dry days, 30 zeros, and then one day it rains a lot, a spike, and then again zero. It's not possible with a straight line. So just keep in mind that certain variables, certain climate variables cannot be reproduced with a straight line. So if we are interested, for instance, in drought are represented by zeros, by rainfall. How can we analyze, how can we make an inductive assessment of drought changes? And I want to give you another example then, which is another example of inductive assessment. It's a very simple, again, solution, which is completely different from a straight line, which is used to characterize processes that are highly intermittent. Temperature is not intermittent. We have observed values every day, and it doesn't assume, it's not intermittent. There are no sequences, long sequences of zeros, so it's relatively easy. So let me just make another example. Inductive assessment. Inductive assessment of drought. Let's focus on drought because it's a relevant example. Drought changes. And this is, the method is called the rank theory. Now, let's suppose that we refer to annual rainfall, which is not intermittent, but it's highly nonlinear annual rainfall. And let's suppose that we have a long time, we have these observations of annual rainfall, And then let's suppose that we have a long drought period. Okay, this is just a schematization. It's not very realistic, but let's suppose that you have annual rainfall, which is more or less constant, and then you have a multi-year drought. So this is a multi-year drought. Multi-year drought. Annual rainfall is characterized by a mean value, which is usually not much affected by climate change. But climate change may increase the risk of droughts. So in the long term, you don't have changes, but you may have an increased risk of long periods with low rainfall. Again, this is a schematization which is not very realistic, but it is simplified, but it gives the idea. You may remember that I have shown you several times the time series of Bologna rainfall. I like it because I think it is very, very interesting. And I think it was in the Earth system. Let's see. I'm not sure it's here. Give me a couple of minutes. It's not here. Let me see. Premise. No, it's not in the premise. It's in the introduction, I think. Not here, just 1 second. I will get it. Climate change problem. Here it is. This is, you see, this is the time series of Bologna rainfall. And you see in gray the periods with low rainfall. The average is more or less constant. But you have these periods with low rainfall. They last for several years. And the question is, are they impacted by climate change or not? Okay. Now, you see a similar situation here, where you have this long period. So what people do here with drought theory is first to compute this long-term rainfall, this long-term average. So let's call it mu. Okay. And then they fix a lower threshold and an upper threshold. Okay, this is mu lower, and this is mu upper. Mu upper. So run theory, it's very simple. What people do is when they get a value of annual rainfall which is lower than mu lower, they activate the drought. So you get rainfall, let me call it annual rainfall, AR, lower than mu lower, they activate the drought. Okay, and then if when annual rainfall is higher than mu upper, they terminate the drought. So the drought here would be activated here and terminated here. And then you have the drought that is n years. Okay, then 3 if n is lower than a given number, capital N of years, like 3 or 5, forget it. Forget it. If n is greater or equal than capital N, compute drought statistics. Drought stats, and typically is frequency, duration, and deficit. So frequency means how many droughts I have per unit time. It's frequency. Duration, obvious, the mean duration of the droughts. And deficit. Deficit means quantify the lack of rainfall during the drought in percentage terms with respect to the average or whatever. And then the purpose through the run theory is to look at the past and see if drought statistics are changed in time. This is another example of an inductive method. Again, the purpose of run theory in the context of climate change is to look at the past and see if drought statistics changed in time. You see that this is completely different from linear interpolation. Linear interpolation here wouldn't be effective for my purposes. So I devised another method. What is in common with linear interpolation here? What is the similarity? The similarity is that I am completely forgetting about the theory. I look at the data and that's it. Some of you are non-engineering students. For the engineering students at the exam, I may go into the details of what I'm talking about today. For non-engineering students, it's just the concept I am interested in. At the exam, I may ask the concept. What is an inductive approach? What is a deductive approach, for instance? To engineering students, I may ask you to provide an example. And the question may be, can you please explain what is run theory? What is analytical? What is linear interpolation with the analytical representation of the straight line, conditions of linearity? This may be questions for engineering students because these questions are technical. And for non-engineering students, I just focus on the concepts. Yeah.
What about capital N, mu lower, and mu upper? About
their values. Okay, I can give you some examples. I saw examples of run theory where mu lower is taken as minus 20% with respect to mu, with the long-term average. So in Bologna, for instance, the long-term average is about 700 millimeters, which means that I activate the drought in a year where I get 560. And for the termination of the drought, I saw people adopting plus 20%. Somebody adopted plus 30%, which is more conservative. I also noticed that if people are focusing on a very large capital N, typically a long-term drought is defined as a drought that lasts more than 5 years. And but if people focuses on longer duration, like 20 years, then they require, for terminating the drought, that there are at least 2 years exceeding mu upper. Because, you know, you may have a drought that lasts 20 years, and you just have 1 year in between with high rainfall. So if you focus on a long-term drought, it's not enough 1 year of abundance in order to recover the system. Okay. Another example of an inductive assessment. Inductive assessment, long-term persistence analysis. Okay, let me give you an example of two time series with the same average. So let's put time here. When I say time series, I mean a sequence of observations in time. In the web pages, there is a link, a Wikipedia link defining time series. When we talk about climate change, very often we talk about time series because we are interested in climate change in time, of course. And okay, so here you have a generic variable. Let's call it W, okay, WT. And let's put a mean value here. And let's visualize two time series. The first one is, for instance, this time series here. Okay, very generic. Second one. So the first one remains around the mean, fluctuations, but it's around the mean. The blue one is subjected to cycles. Remember when we looked at the last week, we looked at the changes of temperature over 500 billion years, and you remember glaciations, etc. And the line of temperature was very similar to the blue one here. You understand that detecting change is easier with the orange line. With the blue line, suppose that you have only a window of observations from here to here. How can we say if this is a change or a cycle? So when there are cycles and we have only few data, it's difficult to say if we are in the presence of a change, in this case a decline, or a cycle. So detecting change is more difficult. Why this is relevant? Think at the global warming. Is it a change or is it a cycle? which means, is it anthropogenic change or it's natural variability? So it is in the presence of cycles, it's more difficult to reach a conclusion. And this is why people are interested in estimating the likelihood of a time series to experience cycles. This is a debate that is very active in the scientific community. Is climate subjected to long-term cycles or not? Of course, one may say, of course, yes, because we know that we had glaciations. On the other hand, is it possible that the global warming, which occurred in 30 years, is explained by a cycle? Not sure, because glaciations occurred with time span of billions of years. Did we experience in the past changes in temperature with the same high rate as global warming? Some proxy records, some climate data exclude it, like the current pace of warming is unprecedented. Other proxy records show similar rate of changes also in the past. So the question is very relevant. And what makes a process subjected to cycles? It is a very simple question. A process is subjected to cycles if it has a strong memory. You get to a perturbed stage, like a minimum, and you keep the memory. The system cannot react quickly, jumping from a minimum to a maximum. When the system reaches a minimum, it remains in a minimum state for a long time. And conversely, when it reaches a maximum, it remains there for a long time. It means a memory of the position, of the dynamics. It is very simple. If you understand, if you think of it, you get to a high temperature and the system remains there for a long time because it has a memory. It remembers. Like, for instance, another example, think of a large river. It gets a flood. The flood lasts for a long time in a large river. It's not possible if you go over the Po River. There is a flood and one day later there is no water. It's impossible. It has memory. Once that the Po River has got very wet, has got a high storage, then this perturbation remains for a long time, is memory. Another way to call memory is persistence of the system in a state, or dependence. Memory is also called in statistics dependence, high dependence. A system has a high dependence from the previous states. So this is why I called it long-term persistence analysis. Long-term because it means long cycle. Persistence because persistence means persistence in a perturbed state. How can we analyze the likelihood in a process of getting cycles? First, you see an analogy with the previous example. A drought can be seen as a long-term cycle. So run theory can be used to detect the likelihood of getting cycles. But there are other solutions. And a second solution, which has a long history in science, is long-term persistence analysis. And before I make the break, it's interesting. Let me unpin the blackboard because we need to go back to the web page. Just 1 second. Okay. In the web page, there is trend analysis, and there is run theory. The figure is not working. I need to understand why. Let me just try to reload it. No, okay. I need to check why the figure of the run theory is not showing up. It will be easy. And then there is the long-term persistence. And there is here a presentation which explains how long-term persistence was discovered. And it was a game-changer discovery in science. And it is a very short one. It's a PowerPoint with no quantitative information. If you are interested, have a look at this Let me see if it is downloaded. Yes, and let me open it. We are not looking at it together, but it's fun. So have a look, and it's a nice story because it explains how a game changer discovery occurred. You need some time, so don't look at it now. And then it is. I think it is interesting. I delivered this presentation in a longer version in a meeting, and then I cut it just a few slides for you. We will anyway discuss again long-term persistence when we come back. Do you have any question before we go for a coffee? Okay, good. Let me close the webcam and the microphone. See you in 15 minutes. Okay, so I hope it's clear why estimation of persistence, of memory, of dependence is important. Because it can help assessing the presence of change and the magnitude of change. And it's also important to make predictions for the future. It's particularly important for the prediction of droughts in the future, because droughts are also originated by these long-term changes. Now, let me introduce to you how we can estimate in a very simple way, provided we have data, the likelihood for a time series for a process to exhibit these long-term cycles. And think at a very simple consideration. How can we detect long-term cycles with another method besides round theory? Round theory is also very simple. But think of a simple approach, because another simple approach, because this is something that we always have to keep well in mind in science, in research. Sometimes there is sometimes we adopt methods that are too complicated, too difficult, too elaborated, while there are methods that could deliver a simpler assessment. The reason why we sometimes adopt methods that are too complicated is that in research in science, there is an usual attitude to try to better understand, to try to go into the fine details, to understand everything. And in order to understand everything, the research of the scientist sometimes tends to be to adopt approaches that are overly complicated. If you want to explain everything, you have to adopt a very complicated model. You understand that. Instead, if you focus on the big picture, if you focus on the technical issue, on your technical requirements, it's easier to identify a simpler approach. Also, keep in mind that in science and research, we have the need to advance in our career. And advance in the career means proposing innovation, proposing new approaches. And therefore, sometimes the researcher tends to look at complicated explanations because there is the need to propose an innovation. If you propose to estimate climate change through linear regression, through linear trend analysis, it doesn't look like an innovation. Okay, now this is to give you an explanation that sometimes when you refer to innovation, you refer to scientific research, sometimes there is this risk, this danger of adopting approaches that are overly complicated. And from a technical point of view, this is a big problem because, as I said, complexity means higher uncertainty. Now, let's try to find a very simple way of quantifying the likelihood of getting long-term cycles. And let's suppose that you want to estimate the average of this time series, the mean value of these observations. And let's suppose that instead of computing the average over the whole length of the data, you compute the average over pieces of data, over small windows. So let's suppose you get this first window here, and here you get the average, okay? Let me call it me. You compute the average here. And then you go on the next window. So this is me 1. And then you go to the next window, me 2. And then the next one, me 3. If you have long-term cycles, you understand that these averages will differ more than the case of the orange line. For the orange line, the average will be more or less similar over these three subsequent windows. If you have cycles, the average will be more changing. So here is the idea, is let's look at the variability of the average in pieces of data. If the variability of the average is large, then I have cycles. If the variability is small, I have less memory. If the variability is large, the variability of the average, I have more memory, more persistence, more dependence. If the variability is low, less memory, less persistent, less dependence. This is very simple because I just need to compute averages. The simpler operation that we may think of is an addition, and then variance of the resulting averages. Variance is standard deviation, is another very simple statistics. In particular, there is proof in statistics which we don't demonstrate, which says that the variance, let me adopt the same symbols as in the variance of x hat. X hat is my average computed over a window of length n, capital N, sorry. This is proportional through a constant c to the length of the window minus 1, which means that the longer the window, the lower the variability of the average, which is something understandable. You know, if you compute this this average over a short window, you have more variability. If you widen the window, then the lower the variability. So there is a demonstration in statistics that variability, the variance of the average, is given by this relationship for no long-term persistence. If you have long-term persistence, then the variance of x hat n is proportional to n to the power of 2h minus 2, where 0.5 with h varying from 0.5 to 1. You see that if h is 0.5, we go back to here. H equal 0.5, we go back to here. If h is greater than 0.5, you get the variance that is decreasing slower. This is a very simple way of estimating likelihood of long-term cycles, and if you end up with an estimation, this is very easy to be made. In R, it's very simple, and if you get h greater than 0.5, we don't discuss why h should be less than 1. Let's forget about it, okay? There is a discussion behind this, which we forget. We don't discuss it. But if h is greater than 0.5, you see that we get a different case with respect to the case of no long-term dependence. And in particular, you see that the variance of the mean decreases more slowly, which means that estimation of the mean is more uncertain, which is precisely what we are expecting here. For the blue line, the estimation of the mean is more fluctuating, is more uncertain. This is a third example of inductive assessment. We forget about the theory here. We just make a computation of the up and downs. That's it. Question?
Can you repeat this last point? So when the estimation of
Yes. Yes. Okay. first, let's focus on the concept. For the orange line, you expect that when you estimate the average of the orange line, is more condensed around a constant value. For the blue line, you expect the average going up and down. Okay. If the average goes up and down, it means that the variability, the variance of the average is higher. This is what you are expecting. Now, the variance of the average is given by this relationship for no long-term persistence, and you see that the variance here, the power is -1. The variance decreases for increasing n, which is what you are expecting. I increase the number of observations, and then I have a more consistent estimation of the average. But for the blue line, I am expecting that the estimation of the average is more uncertain, goes up and down, which means that the variance of the average is greater in this second expression than in the first one, which is what I obtain if h is greater than 0.5. Okay, I hope. We will make an exercise, by the way, on this, and I'm not sure if we can make it on Thursday, maybe, but we will make it. Okay, and so again, this is another example of inductive assessment of what? Of changes due to long-term cycles in data. And these long-term cycles may be the explanation of droughts, as I said. And here I put 3 links of multi-year droughts that occurred very recently. The risk of multi-year droughts is emerging as a consistent threat for modern society. It's not yet clear if it's increased under global warming. It's not clear. So this explains why there is this interest in analyzing data and trying to understand if these cycles have increased recently, if droughts have increased in frequency recently. There are contrasting results. But these are inductive assessment. We look at data, we don't question, we don't ask ourselves what is the reason for the cycles. We don't want to be bothered by these questions now. We just want to find simple approaches in order to understand if changes are occurring and in order to project these changes into the future. Just keep in mind so far, to conclude with our reasoning on inductive approaches, if you don't have data, you cannot use inductive approaches, okay? You have to resort to something different. And now we can pass to the deductive approach. Okay, let me clear the blackboard and let's write as title over the blackboard deductive approaches, which means basically modeling. Theory means theory, and the theory allows us to write models, to build models which can be used to reconstruct past climate and to make future predictions. So deductive assessment. Deductive assessment, which means theory, which means models. As I said, we can use climate models. They are conceived precisely for this purpose. Climate models do not typically reproduce variables that are far beyond climate. So if, for instance, river flow, we need a cascade of models. We need a climate model to generate rainfall, and then we need an hydrological model to generate river flow. If we want to compute the socioeconomic impact of a drought, we need a climate model to predict changes in rainfall. We need an hydrological model to predict changes in river flow and groundwater, and we need a socioeconomic model in order to estimate the damage. So it's, as I said before, a cascade of models. Today we are trying also to incorporate these models in unified solutions, but this increases the complexity. And increasing the complexity, once again, means increasing uncertainty. So it depends on the application to decide what is the best approach that you can use. Any application is depending on local conditions. So you need a careful evaluation, a careful assessment of what you need, what is available in terms of information, and what is the purpose of our analysis. As we did for the inductive assessment, I will give you some examples of deductive approaches, but I cannot give you more than a couple of examples, and therefore just keep in mind that it is a solution that requires a careful assessment of the literature, of what are the available models, and at the same time a careful assessment of the local conditions. Typically, these models, let's focus on the models of the Earth system. So climate models, hydrological models, models that are trying to reproduce nature. They are based on physical equations. Physical equations, why? Because basically these models have to simulate the storage and flux of matters. And the matter may be, for instance, heat, maybe energy, maybe mass of something, mass of water. And storages and fluxes are typically described by the equation of physics. And typically they are conservation equations. Conservation of energy, conservation of mass, conservation of momentum. These conservation equations may be coupled with chemical equations if we are interested, for instance, in quality of air quality. It is a big issue today, the impact of climate change on air quality. But in order to inspect the dynamics of air quality, you need probably also to resort to chemical equations, or biochemical equation, or biogeochemical equations. But in their simple form, in which they describe the storage and flux of matter, typically Earth system models are mainly based on physical equations. These physical equations are conservation equations, as I said, and they are expressed very often in differential form. Conservation equations. And often in differential form. Why in differential form? Because this conservation equation often allow us only to describe the changes in storage and changes in flux. Usually engineers, when we hear about differential equation, which means also the use of integrals, we get a kind of, we get trapped in a kind of depression feeling, because we think that differential equation and integrals are complicated. Actually, I think I already made this reasoning with you. Actually, integrals are just sums and differential equations are just differences, which are the simpler operations that we learn in the primary school. it is integral are complicated just because their analytical form is complicated. But if we use numerical integration, it's just a matter of sums and differences. So you don't have to be concerned by differential equations. This is the moral of the story. So these are, as I said, very often conservation equation. And conservation equation of mass, as I said, momentum, energy. And don't worry if you don't remember what is momentum, it's not a problem. And conservation of energy, conservation of heat, for instance. These are the equations that we can write to describe nature. And of course, in writing these equations, we need to refer to a theory, the theory of physics, and we need to refer to a domain, a spatial domain. We need to refer to a time span, but it's not really much complicated. When the models become too complicated, we may resort to empirical models. Empirical models are just approximation of Earth system models. Empirical models are often characterized by, are often derived by not directly referring to a theory. Like, for instance, the linear model. The linear model is an empirical model. The linear trend analysis is an empirical model. I just assume that the progress is represented by a straight line. It's an empirical model. But if you look at the nature of the model, you can identify a connection with the theory, a connection with the more complicated interpretation. So my suggestion is when you use empirical models, try to understand, to decipher the connection with the more complicated model. We will provide some examples, okay? And focusing on this connection is important because it allows you to get more convinced about the solution that you are using. It's very important to increase your confidence in your results. Okay, so let's start with climate models. And climate models, there is nothing that I need to write on the blackboard. Let me just unpin the blackboard for a moment. Climate models, let me go back to our web page. A second. It's working, okay. Tutorial of climate change adaptation. You have a link here, which is called climate models, which is the next one in our discussion, in our, list of links. And I will not give this lecture, but I leave the link there because it's a narrative description. It describes how climate models are structured. And it's not a matter for your exam, but I leave the link there because, as I said, it's simple and I think it may be interesting for you. Climate models, so we are not getting into the details of how they work. I just want to say a couple of things. First of all, by referring to the web page that I just wrote for you. First of all, these models are very computer intensive. They are numerical models. And we need to refer to climate models as users. We don't need to develop a new climate model. It is something that is not for engineers. And I think it is just enough that we understand how they work and we understand that they are very computer intensive. And also we have to understand that their level of detail is not very fine, which means that, for instance, you cannot generate rainfall in Bologna at the point scale. They are working on grid, on spatial extension of about 5 by 5 kilometers. So they generate rainfall, for instance, over an area of 5 by 5 kilometers, not in the point, because, I mean, they are very computer intensive, and describing the details at the very fine location, it is something that is still not possible. This is the first thing that we have to keep in mind. There are several websites, several public domain repositories where you can get climate predictions. And one example is the Copernicus Climate Data Store. So, yes, the screen is shared, which is this one. You need to register, but it is very easy, and it's open, it's free. And then you can download climate of the past and climate of the future data, even at the point location. So, for instance, if you give the coordinates over Bologna, they give you the rainfall for Bologna, but this value actually is averaged over an area of 5 by 5 kilometers. It is easy to access it. To retrieve the data is not very easy. Some skills are required in terms of coding, but yeah, this is possible. And so besides this, sorry, let me go back. Another thing that we have to have clear in mind is the uncertainty of these predictions and reconstructions. So, for instance, if you compare the rainfall in Bologna with the observations in Bologna for the past 150 years, you see that there is a mismatch, even in statistics. There is uncertainty, there is an error. And this is why the scientific community has proposed several techniques for correcting the predictions. I just want that you are aware of this. And we don't need to go into the details. I just want that you are aware that climate models are often corrected. And in order to make the correction, what they do is to compare the climate of the past with the reconstruction given by the model. It is something similar to linear interpolation, if you think of it. And this is only possible when you have historical data. Where you don't have historical data, it's not possible to correct these models. And furthermore, let me say that when you make a correction, you cannot correct everything. You just correct the features that you believe need to be corrected. For instance, if you see that the average predicted, the average rainfall, the average temperature predicted by a model is wrong, you correct the average. But what about variability? What about the long-term cycles? And this is something where the models are typically wrong. They are not able to capture the observed long-term cycles. And this is a problem. I just want that you understand that the picture is a bit complicated. It's not just a matter of saying climate models are better or inductive assessment is better. When we talk about changes in climate, until we remain at a quantitative level, at a qualitative level, everything is more or less clear. Climate is changing, most probably for human impact. Climate change means that temperature is increasing. Rainfall, we don't really know, but probably the extremes are increasing. But when it comes, once again, to numbers, how much will increase the temperature by 2050 if we decrease our human emissions by 30%? This is still a question mark. This is still a challenge. So I just want that the situation is clear to you. Now we will see some examples of models. I think it is very interesting, as we did for inductive models. I want to give you a couple of examples of Earth system models. One very simple, extremely simple, and another one a little bit more complicated. Just two examples. I could give you trillions of examples because you understand we have a variety of climate models, a variety of impact models. So I just want to give you some examples, and then we will try to draw a conclusion on how to get oriented. By always keep in mind that our mission is finding solutions. It's not communication. At least it's not our primary mission, communication. So the reason why we discuss uncertainty is that we need to find solutions. And we have to adopt, of course, a different attitude when we discuss with the public, when we communicate. Communicating uncertainty is a big challenge, but discussing uncertainty among technicians, it's easier. Okay, so I want to give you a couple of examples, and I hope you bear with me if I refer to rainfall runoff modeling for the very reason that I already mentioned to you, that climate impacts, most of them are transmitted by the water cycle. And therefore, what is extremely important is that we can translate changes in rainfall to changes in water. Water changes can be river flow, can be groundwater storage, can be water available into an artificial reservoir. In order to make finding solutions for climate change impacts, we need to make this translation from climate change to water change, from climate change to temperature change. This is not really an hydrological model. When we talk about temperature, it's closer to a climate model, but still is very relevant to hydrology. So how can we make this translation, this interpretation of the transformation from rainfall to runoff? And I want to give you a very simple example to start, because in some cases, this translation may be very easy. So let me give you the first example. The first example is the first rainfall runoff model that was proposed by the scientific literature. Let me pin the blackboard. The first rainfall runoff model proposed by the literature dates back to around 1850. It's called the rational formula. Let's write around 1850. The rational formula. And it was proposed as an empirical formulation, but it is very easy to find the connection with the physics of the process. So for this reason, I think this is a very interesting example. The rational formula. First, it's quite clear to us that water depends on rainfall. Water in the Earth system depends on rainfall. It's quite clear. River flow depends on rainfall. Groundwater storage depends on rainfall. This is obvious. However, we realized this connection only 400 years ago. Until up to 1600, people didn't understand that water availability was conditioned by rainfall. You may say, how it's possible? It's so clear. It's so clear. When I get rain, I get water for irrigation. When I get too much rain, I get a flood. Yes, it's clear to you because now you have good communication means. But can you think of people living around the Nile River? They got flooded with no rain because the rain was in Ethiopia, which was, almost another continent. And in Egypt, they didn't get any rain, but they got the floods. So what was the explanation that they got for this evidence? The explanation was that water was coming from somewhere in the underground. And this was the reason, the motivation for floods. Up to 1600, there was a significant part of the scientific community that was convinced that floodwater was coming from the underground. It was an emergence of water from the underground. And then it was an Italian monk, Padre Benedetto Castelli, who realized by measuring rainfall on his monastery and the water level in the Trasimeno lake that was quite a bit apart, but he went there and measured the changes in water level, and he found a consistent connection with rainfall. And he was the first one postulating this theory that rainfall was driving river flow, rainfall was driving the water cycle. And this gives also to you the idea of the young age of hydrology, of the water cycle science. Our understanding of the water cycle is very young. And this is why people didn't collect data in the antiquity. Okay, so basically the first scientists understood this connection, and what they assumed was a linear connection. So they first wanted to try to explain the peak flow, like the floods, because the floods were the major concern. It was not really water security for them, because they established cities around rivers where water was available. And they didn't have much problems of pollution. Actually, in some cases they had, but it was not a big problem. And therefore, they were not concerned by the lack of water. They were concerned by floods because they went close to the rivers and they got flooded. So the idea was to find an explanation, an analytical estimation of the river flow Q, and this was the peak flow. Peak flow. They wanted to find a number for the peak flow. It is a very similar situation to our situation now. We want to find a number for change. They didn't have any idea of how large was the peak flow. They had no measurements. It's very similar to what we are experiencing now. So they said, okay, it's related to rainfall. Let's suppose that this is related to rainfall through a constant. This is a constant, like the linear model, okay? It's a constant times rainfall intensity. E is rainfall intensity. Rainfall intensity. But they also understood that there must be some more, which is the area of the catchment. Okay, so let's include it with the term A. When you refer to a river gets water from a catchment. The catchment is the area, the drainage area of the river. The river drains water from the catchment. And therefore, they understood that the larger the catchment, the larger the peak flow, of course. Because rainfall gives the input, gives the volume of water. But the volume of water must be multiplied for the area, the drainage area of the river. So they got this relationship. Let's make a dimensional analysis here. So Q, dimension of Q. Q is river flow. It's volume of water per unit time. Cube of a length, volume, divided by time. This is how river flow is defined. Beware, you may got a question in the quiz, what is river flow? Beware of your background. I'm not redefining river flow, but beware of what river flow is. Okay. Okay, C is dimensionless. It's a constant, dimensionless. Rainfall intensity. Rainfall is expressed, usually has a length, but intensity means length over time. Rainfall is depth of water during a rainfall event. Good. Area is square length. If you look at the dimensional analysis is dimensionally consistent. The rational formula is dimensionally coherent. So length cubed divided by time is equal to rainfall is here. Length divided by time times area, length square. It's consistent. This formula is empirical. They just realized that river flow depends on rainfall intensity and the area drained by the river. And then they introduced a constant. It's very empirical, but you can recognize here conservation of mass. It's clearly conservation of mass because it says that you get a volume of rainfall because rainfall intensity times the area, it's volume of rainfall per unit time, which is conserved here through a constant. It's conservation of mass. This is what I mean for seeing the analogy between the empirical model that must be coherent with the physical interpretation, with our theory. A model cannot go against a theory. It means that either the model or the theory are wrong. There is inconsistency. It is very fine to use empirical models. In engineering, we need empirical models. But if we want to be innovative engineers, if we want to be the engineers for the 21st century, we need to be able to see this connection. The empirical model, if it is a good model, it must have a clear connection with the theory that we need to understand. If it is a good model, and we need to use good models if we want to bring innovation, if we want to invent revolutionary solutions, we need to use good models, and for this reason it's important that we can see the connection with the theory. I am not done with the rational formula, but I just want to close for now with this hint, this input for your thoughts in the next few days, if you have time and if you are passionate of this subject. Questions? Okay, we will see each other on Thursday. It's very likely that I propose some short exercises, but still these exercises will be tightly connected with what I lectured today. Grazie, thank you very much.